Hello class, I want to share a little bit about this novel development in the fight against COVID-19, which is the successful completion of phase 3 clinical trials by two types of antiviral compounds being basically put on the market by Pfizer and by Merck respectively. And so, as you know, the first line of defense against COVID, just like any virus, is vaccine development. However, there's still a place for antiviral therapy for a number of reasons. First of all, not everybody's getting vaccinated. And second, many people cannot mount a sufficient immunity even upon vaccination. So the problem with development of antiviral agents is that, as we discussed during the module, antiviral agents tend to be specific for the virus in question. But having said that, over the years, scientists have developed a number of antiviral agents that target certain, broad targets within a virus, and that gives us a chance of looking at cross-reactivity. And that's what Merck did. So before we start, by now probably everybody is familiar with the life cycle of coronavirus. And so what happens is that we have a viral particle which is surrounded by a membrane in which we have transmembrane proteins, so the infamous spike protein. And then we have other proteins, basically partly in the membrane and partly like N, that helps packaging the genomic material, which for SARS coronavirus 2 is single-stranded RNA positive. So what happens? The viral particles approaches the host cell and binds to ACE2, which is the angiotensin processing enzyme 2, which is basically the enzyme that cleaves angiotensin and has a role in regulating vasodilation and bronchodilation. A version of this enzyme is actually associated with the cell. And that is the version, of the membrane, so it's a membrane-anchored version. That's a version that is targeted by the spike of coronavirus. So we have a binding of the receptor in this stage. And then we have a transmembrane serine protease, TMPRSS2, which also is part of the mechanism of action. So what happens? So we have, again, recognition of the virus attachment. We have a formation of endosome, and at that point, basically TMPRSS2 cleaves this famous furin cleavage site in the spike protein, and that changes, basically starts a rearrangement of the spike protein. We have viral fusion of the viral membrane with the membrane of the endosome. We have uncoating. And then we have a couple of things happening. First of all, because this is a single-stranded, positive sense RNA, that gets immediately translated into protein. So we have this open reading frame 1A and 1B. Then in turn get processed by viral proteases into, a variety of viral proteins, including the N protein, which is in charge of helping, replicating the RNA. And so at this point, we have the encoding single-stranded RNA that needs to be basically replicated into, first by doing the negative-stranded, synthesizing the negative-stranded RNA on this template, and then again we form new positively stranded genomic RNA. So that in turn basically gets processed, and the proteins get made. The viral RNA, the viral polymerase rather, chops up the the product of genomic RNA translation. So the open reading frame 1 and 2, and so we form new particles, new viral particles that then go through the Golgi apparatus, where the spike protein gets glycosylated, among other things, And then by exocytosis, the virus is released in the outside. And so what are the potential targets for coronavirus? Well, we have, entry inhibitors. We have inhibitors of the host protein of temperase. We have inhibitors of the viral protease. We have viral inhibitor of the RNA-dependent RNA polymerase, which is what we'll see today. And then we also have compounds potentially that, basically inhibit assembly and maturation of the virus, and so exocytosis. So the approach taken by Merck has been to target the RNA-dependent RNA polymerase. And so the compound was initially discovered at Emory. It was part of a series of compounds developed against the first coronavirus, the first SARS. So the target again is a polymerase, the RNA-dependent RNA polymerase. Is, as you will know by now, is a nucleoside analog, and it's a prodrug for more than one reason. Again, all the nucleoside analogs need to be phosphorylated to nucleotides, and so that's part of what, why all of them are going to be prodrugs. But this is also a prodrug in another sense, because basically we have this ester moiety that needs to be cleaved in order to have the active form being unmasked. So this molnupiravir needs to be metabolized to the active form. What's the action? Well, we'll see a little bit in the next slides, but basically it's incorporated in the RNA and the viral RNA and causes a couple of issues. One is, the chain termination of the new RNA strand synthesis. And the other one, we have also, misincorporation, miscoupling then, and error propagation. So the side effect for this nucleoside analog, just like most of those, is a relative lack of specificity. So in higher doses, it can also inhibit, the host translational machinery. And so we have a cytotoxicity. So let's see how we go from the molecule to the active site. So the active form. So again, we have cleavage of this ester moiety, which unmasks the the functional part of the nucleoside, and then nucleoside needs to be triphosphated by host enzymes, and so that happens 3 times, and then we have the active molecule. One important thing about molnupiravir is that it's orally available. Okay, the other interesting thing was basically published very recently in the synthesis of this compound. As I said, this compound had been developed a few years back for SARS coronavirus 1. In the intervening years, Merck has done a lot of work in coming up with a synthesis that is easy and is also environmentally friendly. And so what they use is actually what they call an enzymatic cascade, starting from basically ribose and the ester anhydride. And what we have, basically phosphate cost, basically, in this reaction, we generate the prodrug directly. And so this is done with one single intermediate that gets isolated and then gets esterified. There are 3 steps. The overall yield is 70% almost. And so it's very high yield, very environmentally friendly, and scalable. And this is beyond the purpose of this class, but interestingly, the enzymes used for the synthesis have been re-engineered to carry out the synthesis most efficiently. Okay, so at this point, all we need to do is a single chemical treatment. So this is the intermediate on the synthesis that gets isolated. Then we have a chemical treatment to make basically a oxime functional group here instead of the carbonyl group. All right, so let's look at the mechanism of action for this compound, and remarkably we already have the structure of the compound bound to the RNA-dependent RNA polymerase of coronavirus. And so here we have basically the template, RNA template in blue, the product in red, and then basically 2 accessory proteins and an sp12, 8, and 7 that form part of the polymerase. And so what happens is that when we have incorporation of molnupiravir, which is this one here, in the base pair in between the template and the product is kind of mismatched. And so we have either MA base pair or a MG base pair. And this is basically a close-up of what is going on in terms of hydrogen bond formations. And that's what, basically the interaction looks like. So we can have incorporation of molnupiravir on the other side of our template in the product, and this can be paired both with A and with G. And so what happens then is that this mispairing affects the functionality of the RNA-dependent RNA polymerase. And so here, for example, let's have a look at what's happening. So we are starting from the positive stranded template, and so we need to make a product that is now the negative stranded RNA, right? And so what happens here, we can have misincorporation of M opposite to both A and G, okay? And then again, one of the possibilities to simply to have then at this point also chain termination when molnupiravir is present. But even if the RNA template, basically the RNA product rather survives the molnupiravir incorporation, what happens next is that we have now, our negative stranded becomes the template for the synthesis of more positive stranded genome type RNA. And every time we have molnupiravir incorporated in the new template, then we have either A or G being incorporated pretty much randomly. In addition, we also have additional incorporation of M. And so now we have both templates and products that carry basically errors. And so as a consequence, also the viral proteins will be impaired.